Well, hello everybody. Today we're going to talk about sequence parallelism. And that's the first time I said parallelism without hesitation. So, let's quickly overview what we covered before and where we stopped. So we had this marvelous pipeline where we did tensor parallelism, and first we did column linear split, then we did row linear split, and then we did all reduce to get the final result. And in terms of timeline, it looked roughly like this, where we kind of enter this TP region, we do all these splits, then we do all reduce, and then after the all reduce, we do layer norm. And the kind of big bottleneck here is this all reduce, because we can't really overlap all reduce with anything else. And for the self-attention block, as we can remember, the split worked, well, roughly on each GPU, we roughly calculated self-attention for each one of the heads. I say roughly because, well, we can have a different number of GPUs and different number of attention heads, but nevertheless, we can kind of imagine that a single attention head is being calculated on a single GPU. And in terms of memory, with sequence, well, tensor parallelism, we managed to decrease the amount of memory required for model parameters, gradients, optimizer states, but we're still struggling with long sequences, and specifically with activation memory for long sequences. Why is that? The culprits are, well, based on the book, layer norm and dropout. And when I first read it, I kind of stopped there for a bit, like, why dropout? But we'll get to that later. First, let's once again remind ourselves how we split and what we split. So we have a sequence with various tokens, red, green, blue, and then this sequence of tokens gets transformed into matrix. Well, actually tensor, but that's details, that doesn't really matter. So, like, we can imagine a matrix where for each token we have an embedding of size h, and we have multiple of these tokens. And what we covered before is that we can split in the, well, by the hidden dimension, by the dimension of our embeddings, and kind of store the whole sequence, but like part of the, like the whole sequence with only a part of this hidden dimension on one GPU and store the rest on the other, or like split it into multiple pieces, roughly. And we're going to talk about why roughly, but that's kind of a mental model. And now, for some operations, we need the entire hidden dimension, and we don't really care about storing the whole sequence. And this is what we're going to cover today. It's called sequence parallelism, and where we kind of go from this split, where we have the whole sequence, but only kind of we don't have access to the entire hidden dimension at all times, to having access to the entire hidden dimension for every token at all times, but not having access to the entire sequence. And to do that, well, we established before that the culprits, according to the book, are layer norm and dropout. Let's remind ourselves what layer norm is. So layer norm, it's, well, we have this, well, not so sophisticated, but still a mathematical equation where we have the inputs that will be x, our activations. We deduct the mean of these inputs, the activations for a single token. Then we divide it by the standard deviation, and then we multiply it by our learn parameters. That would be gamma and beta. Beta? Whatever. And if we leave aside the mathematical side of things and try to kind of picture it intuitively, in black we have the original activations for the layer for a single token, like across this H dimension, hidden dimension. And what we want to get before, like this stuff, the before we multiply by gamma and add beta, we want to kind of squish the input distribution, and we want to center this input distribution. So hence we want to kind of standardize it. And as a result, when we subtract this mu, we kind of move our original distribution and center it around 0. And then when we divide by standard deviation, we kind of normalize the width of our distribution. So now the standard deviation of this distribution is 1. And that means that whatever we learn later, gamma and beta, they are going to be, we will be able to universally apply these learned parameters to any token, any input, to a token with any input distribution, because first we standardize it, and then we kind of, once we have standardized distribution, we can apply the same kind of learned, we can extract the same information from the standardized stuff. That's how, at least that's how I imagine it. And once again, it happens along the last hidden dimension. And that's, that kind of didn't sit right with me. So at least like mental model, I mean, like I get how lay norm works, but what really bugged me is how do we get the save memory? And if we split by hidden, if it's applied by hidden dimension, then like what exactly, why do we really need to have the entire layer? Why do we need to collect all of the activations? And what are we missing in the current pipeline? So let's get back to it. This is what we get with tensor parallelism. And this is where we basically stop, and that's what in my mind we really want to optimize. So first we do tensor parallelism, we do this column linear split, we do row linear split, and as a result, we get these two matrices. They are the same size, and they kind of have partials of our final matrix. And that this is the final matrix that we want to, if we don't do sequence parallelism. This is the final matrix onto which we want to apply the layer norm and the dropout. And basically the most expensive operation here is all reduce. So first of all, we want to, well, somehow make this all reduce a bit more efficient. Well, and second, we have all these matrices, right? So we want to do something about that. And when I asked ChatGPT, well, not ChatGPT, it was actually Gemini, but who cares, to visualize it for me, that's what I got back. So we kind of shard across hidden dimension, and then on the first GPU, like if we do it across two GPUs, then on the first GPU, we kind of get only half of the features. On the second GPU, we get second half of the features. But really, I'm not sure that truly corresponds to the picture that we saw before. Because, as we can see, I mean, like, it kind of works if we look at the left side of the picture, right? Where we split the weights right here by columns, kind of. Or maybe like when we get back the columns, yes. Here, like, if we talk about activations, then like, yes, once we do the column linear split, we get back activations only for a single column. But then when we do row linear split, we get back the whole matrix. So, and as we can see, the size of each one of these matrices that we kind of parallelized is the same size as the size of the output matrix. So that's kind of, that made me raise my eyebrows, and I tried to torture ChatGPT to get more insights. And here's what I got back. So what we really want to get, well, the end goal and the end result is that with standard tensor parallelism, after the all reduce, we get the same output on each one of the GPUs, so like the whole matrix. And with sequence parallelism, if we split, like we divide the sequence in halves, for instance, as a result, we get back only half of the matrix, only half of the final matrix, which kind of makes sense. And that means that the correct mental model is that instead of kind of, when we do split by the hidden dimension, instead of storing like half of the features, it's like we're storing partials of each feature on each GPU in the end. And now let's kind of remind what we covered before, like our original picture, how we did tensor parallelism. So like we did this column linear split, we got back columns, then we did row linear split, we got back all these partials and we summed them up. Let's zoom in. So this is the part where we mostly interested in. And if we don't do the sum across all of the partials, but we kind of be smart about it and we do the sum, but at the same time we kind of shard the result across all of the GPUs, this is what we're going to get. But we still have this, right? So at some point, we still have to store in the memory of each GPU, even if briefly, we still have to store the entire matrix. So even if we kind of be very smart about how we like split the data here, like data meaning activations, even if we're being really smart about how we split the activations here, it still doesn't, we still have to calculate this entire matrix at some point. And that means that even if we discard it later on, we still kind of, at peak times, have to store activations for the entire matrix. And well, we can imagine that maybe we can be smart about it and maybe we have some other data that we discard later on, but still, like at peak times, it might be the case that we get out of memory because of like this huge matrix where we store all of the activations. And that got me thinking even further. So can we do something about it? And to my best understanding, the trick to make it work is that yes, indeed, we still store the partials for the entire matrix of activations, but when we do the calculation after the row linear split, we don't really calculate the entire matrix. Well, we first calculate maybe only a part of this matrix, whether it's by row, whether it's by column, whether it's like by tiny fractions of this matrix. So we calculate only the part of this matrix, and as soon as we get the part of this matrix for each one of the GPUs, we immediately stream the result, and we immediately discard the result from the memory if we don't need this result. So for instance, if we calculate this guy, like this small like part of the matrix, well, for this GPU we store it, but for this GPU, because we need kind of to send this block to the first GPU, right here, we calculate it and we discard it straight away. So it's called kernel fusion, and to my best understanding, this is like a fairly complicated process, but basically, the idea is that instead of calculating the whole matrix, we do it in chunks, and as soon as we calculate the chunk, we immediately stream it to the GPU that needs it and discard the data from memory. And now, once we covered how we can make layer norm work efficiently and why we need to store the activations for the entire hidden dimension, dropout, like, why do we even need to have the entire hidden dimension for the dropout? Dropout is applying a randomized mask to our input, basically by assigning some values in our input tensor, input matrix to 0. And I don't see anything that could prevent us from kind of sharding this randomized mask across multiple GPUs and then applying the dropout to each one of the shards independently. And when I tortured ChatGPT and all other various resources in the internet about it, it seems that per se we don't really need to kind of have all activations to apply dropout. The problem is probably with kind of correctly sharding the randomized mask across the GPUs. That's first, but that's solvable. And second, it's kind of not even a problem, but we still need to solve the layer norm thing, right? And if we solve the layer norm thing, if we still aggregate activations for the layer norm, then it's just easier to, since we already have this data, it's just easier to do the same for dropout. So since these operations, they come sequentially, and since we already need to gather activations for the entire hidden dimension for our layer norm, it's just convenient and easy to apply dropout for the entire hidden dimension. Because basically that's where the dropout is going to be applied, right? So since we already have the data, it's just easier to do it that way. But technically, we don't really need to have the entire hidden dimension to apply dropout. And that's how kind of our final pipeline. So before we had these tensor parallelism blocks for self-attention and then linear blocks, and we kind of skipped dropout and layer norm. And now we do tensor parallelism for our self-attention and linear blocks. And then we do sequence parallelism for our dropout and layer norm blocks. And well, intuitively it looks something like this, right? So this is our tensor parallelism, and this is our sequence parallelism, where we kind of split the activations differently and then process them along the split them along the sequence dimension. And the final pipeline, that's a screenshot directly from the book. I'm not going to try to read all the text together. If you want, you can go back to the book. And I think that we kind of roughly covered everything that happened there. So basically, once again, we have sequence parallelism. Well, let's start with tensor parallelism. That's what we know, right? We have our activations. We do row linear split. We do column linear split, and then we do an operation called I think it's called reduce scatter. But yeah, so we call reduce scatter to at the same time aggregate activations for our final output, but also split them across the different dimension. This time it will be sequence dimension, and we get back different shards. So now on each GPU we have shards, like maybe for the first half and for the second half of the sequence. We apply dropout, we apply layer norm, and after layer norm, once again, we do another kind of gather operation where we collect back our activations that we sharded before across the sequence dimension, and we reshard them across the hidden dimension. And we have this lovely table to keep track of what is sharded at each point. So once we enter tensor parallelism, our hidden dimension is sharded, but our sequence dimension is full, like column linear split, right? It's still sharded. This stuff is full. And then, well, yeah. Once we exit this tensor parallelism stuff, we can, in this table, we can clearly see that kind of hidden dimension is full and sequence dimension is full. But the devil is in details, and as we already saw, we can be smart about how and when we calculate the final matrix. So that means even if the hidden dimension is full, we still get to dynamically calculate and discard the data that we don't need. And then when we enter this sequence parallelism region, our hidden dimension stays full, but our sequence is sharded. And if we look at the graphs of memory consumption, we can see that our activations no longer grow that fast with the sequence length, and to my best understanding, the more GPUs we have, the more kind of sharding we could achieve along the sequence dimension. In terms of efficiency, we now have two different operations all together when we transition from the sequence parallelism to tensor parallelism, and then reduce scatter when we transition from tensor parallelism to sequence parallelism. But it's kind of, in terms of efficiency, it's kind of the same as if we did only tensor parallelism, because, well, here instead of all together, no, actually, I think that here we would have kind of reduce, right? We would have all reduce, and all reduce in terms of efficiency, it would be roughly, it would be equal roughly to the same amount of communication. And finally, if we take a look at efficiency, like from the throughput perspective, we see that sadly, tensor parallelism and sequence parallelism, even with sequence parallelism, is still not a silver bullet. So when we increase the number of GPUs across which we shard, because of these guys, which we can't really overlap with anything, we get kind of a huge tax on the parallelization. So with 32 GPUs, we get roughly half of the throughput per GPU. But on the bright side, we get to increase our batch size, and I still don't get why it goes from 40 to 100. In my view, if it kind of, I don't see why it shouldn't go to 80. So it's like 10, 20, 40, 80. Maybe it's a typo, maybe I don't understand something. And finally, this approach still has its limits. With very large sequences, we still blow up here in the tensor parallelism region because our sequence is not sharded, right? So if our sequence is very, very large, we can still have not enough memory on each one of the GPUs to hold the entire sequence in memory, even though the hidden dimension is sharded. And internode connectivity tax for big models is quite it's quite high. So as we can see here, it's the tax for 3B model, and to my best understanding, if the model size grows larger, the tax that we pay gets larger. So this is it. And do we have any questions?
Thank you so much. Can you please go back a few slides to where the layer norm and dropout were mentioned in the diagram?
This one.
Here, yeah. I see there is an arrow going in between them with a plus sign. Is this like the skip connection?
Yeah, I think it's a residual connection.
Uh, so this has to happen also in a sharded way, right? But because it's coming from another SP, that means it's already sharded properly in the same shape.
Yeah, I think so. I mean, like, as long as it's sequence dimension, it should be fairly easy to kind of do the residual stream, right? You just keep track of which token it is and just apply the previous activations, kind of, well, combine previous activations for this token with the new activations.
Mm-hmm. I'm just thinking, like, what does it mean for memory usage? So if you have to
Well,
keep it
probably
around.
you have to keep track of the activations from the previous layer, right? And that's it.
Mm-hmm.
But you still have to keep activations from at least one of the previous layers anyway. Because when we do backward pass, we need activations for the layers, right?
Mm-hmm. Mm-hmm.
So and like we discussed before that we could do checkpointing,
Mm-hmm.
and recalculate activations on the fly. But still, even with checkpointing, we still store activations for at least some of the previous layers, so it shouldn't be that big of a problem.
How does the backward pass even work in this case?
Um,
Says all the same operations have to happen in reverse.
I guess so, yeah.
So the whole SPTP sequence is reversible.
I mean, I don't see why it shouldn't be.
Yeah, I'm just understand it. I'm just trying to internalize it. Okay.
Mm-hmm, sure.
Uh, so at any point in time, you need all the inputs and then outputs, and then when you go backwards, you need the outputs and the gradients, and then yes, sounds great. I
Anything else?
think we're all good.
Alright, guys. I guess that's it with the questions. So, see you next time for context parallelism that should help us to overcome these issues.